Hello, I want to talk to you about mathematics. Hendrik van Malhem, Jeroen Skilevart and me, we wrote an article together and we already uploaded it on archive, so if you're interested you can read it if you want. And in this video I would like to explain to you the basic concepts that are needed in order to understand this article. So I will explain to you how to define buildings as simplicial complexes. I will explain to you what groups of projectivities are, and I will tell you a little bit about the group theoretic consequences of our research and how the geometric things that we've been doing, how they are connected to certain algebraic concepts. This will all be very not so detailed, so it will not be possible to understand everything in detail just with this video. Even if you read the full article, we can't explain everything in there. There's just not enough space, but we give a lot of references, and if you're very interested you will find all the necessary references, and then you can read a lot and then at some point understand all the details. But just so you know, with this video you will not be able to understand all the details, except you already know a lot of stuff about all these things. So like I said, this video is not about explaining everything in detail. It is not about explaining our article in detail or anything about the article really. It is about explaining the basic concepts that we use in our article, such that if you then go and read the article you may have an easier time. And it is about to update you on our research. And like I also said, our results, this is all joint work with Hendrik van Malhem and Jeroen Skilevart. So there are two different ways of defining a building. You can either define a building as a chamber system with certain properties or as a simplicial complex with certain properties. I've talked about the chamber system viewpoint before. It's basically you have a Coxeter system, so a Coxeter group and a generating set for the Coxeter group. Then you draw the Cayley graph for that Coxeter system. And then, following certain rules, you can glue together these Cayley graphs, always for the same Coxeter system, and then you can obtain a building, very roughly speaking. And with the simplicial complex view, it's a bit similar. You again take a Coxeter system, but then the first thing is to define a simplicial complex for that Coxeter system. And this is also called then the Coxeter complex. And then if we want to obtain a more interesting or a thick building, then we take these Coxeter complexes of that given Coxeter system, and again following certain rules we glue together these Coxeter complexes. And then we obtain a building in the simplicial viewpoint. So either way, we start with the Coxeter system, construct something out of it, and then glue the things together. And I will now describe to you how to do everything with the simplicial viewpoint and how a Coxeter complex is defined. First, quick reminder what a Coxeter system is. Let I be an index set, then we can define a Coxeter group by saying it is a group with a presentation. As generators, we take the index set I, and as relations we have ij to the power of mij for all ij in I, and whenever mij is not infinity, and we want that mij is always equal to mji, we want that mii is always equal to 1, and whenever we are not looking at mii, but mij for I not equal to j, then we want that mij is greater or equal to 2, a natural number, and it is also allowed to be infinity. And then this is called a Coxeter group. And then when we write a tuple consisting of the Coxeter group and the index set I, then we call this a Coxeter system. Given a Coxeter group, we can always draw a Coxeter diagram that contains all the information about our group. And we can do that by drawing a vertex for every generator, so for every element I and I. And if we have two vertices, I and j, then we connect them by an edge if mij is strictly greater than 2, and we may draw a double edge if mij is 4. And if mij is greater than 4, then we label the edge by the mij, the number that is mij. A nice example for Coxeter group is the symmetry group of a regular hexagon. There we have two different generators. We can call them G and H. And as relations, we have G square, H square, and then GH to the power of 3. And with that, we get 6 different elements in our Coxeter group. That is the identity GH, HG, GH, and then GHG, which is the same as HGH. So this would be an example for a Coxeter group. We can also draw a Coxeter diagram, of course. And in general, it is the case that Coxeter groups are generalizations of symmetry groups of regular hexagons, and they also include the symmetry groups of the Platonic solids. Like I said, given a Coxeter group, we can always draw a Coxeter diagram that contains all the information about our Coxeter group. And if in our Coxeter diagram there are no double edges and also no labeled edges, so mij is never greater than 3, then we call the Coxeter diagram simply laced. If the Coxeter diagram is connected, then we call the Coxeter group irreducible. And it is actually the case that finite Coxeter groups are classified, and they are classified using these diagrams. So you can draw a list of all the different diagrams that correspond to finite Coxeter groups. We have a complete list of them. And one reason why I am interested in Coxeter groups is that if we look at this list of the finite Coxeter groups, then for some of them it is the case that thick irreducible spherical buildings exist. And these buildings are exactly what my research is all about. I promised Coxeter complexes, so let's talk about Coxeter complexes next. So we are given a Coxeter system, and we will call the Coxeter group W and the index set or the generating set I. First of all, if we take a proper subset of I and we call it J, and then we look at the subgroup of W generated only by the elements in J, then this subgroup is also called a parabolic subgroup. If we remember our example of the Coxeter group, that is the symmetry group of a regular hexagon, there our index set consists of only 2 elements, G and H. And if we want to look at the proper subsets of this index set, then we can only have like the set that only contains G and the set that only contains H. And now if we look at the groups that get generated by this subset and this subset, then in one case we only get the identity and G in our group as the group elements, and in the other case only the identity and H. So for this example, these 2 groups would be our parabolic subgroups. And of course one can also take as a subset of the index set just the empty set, but then it's even less interesting because then we only have the identity. So that would also be a parabolic. So 3 different parabolic subgroups for that example. We call a parabolic subgroup maximal if the cardinality of the index set I minus 1 equals the cardinality of J, so the proper subset of the index set that we took out. In our example, our I had cardinality 2, and if we take out the subset that only contains G, then this is cardinality 1, and 2 minus 1 is 1. So this would then yield a maximal parabolic subgroup. Same with H. And if we look at the empty set as a subset of our index set and look at the group generated by this, this would yield a minimal parabolic subgroup. The minimal parabolic subgroups are always when you just have take as a proper subset the empty set. This is always the minimal parabolic subgroup. If we now take any group element W in our initial Coxeter group big W and we multiply it from the left with a parabolic subgroup, then this is called a standard coset of W, our initial Coxeter group. Let's look at our example again. Look at the parabolic subgroup only generated by G, and then take some element from our initial Coxeter group, say GHG, and now we multiply it from the left with this parabolic subgroup. So the parabolic subgroup, the elements that we have in there are G and the identity. So if we now multiply GHG from the left, then one time we get to GHGG, but GG is just the identity again, so we are left with GH in that case, and then for the identity we just get GHG. So then the coset that we get consists of GH and of GHG. So how do we get a simplicial complex out of this now? We say that we draw a vertex for every coset of a maximal parabolic subgroup, and we draw a maximal simplex for each coset of the minimal parabolic subgroup. As I've said before, the minimal parabolic subgroup is always just the group, the trivial group, only the identity. And now if you think about what are the cosets of the minimal parabolic subgroup, so you have just the identity, and then you can multiply each group element in the initial group once, and then you just obtain exactly the group elements of the initial Coxeter group again, which means that we draw a maximal simplex for each group element in our initial Coxeter group, basically. The maximal simplices we also call chambers. So we draw vertices for cosets of maximal parabolic subgroups, we draw maximal simplices for cosets of the minimal parabolic subgroup, and then we draw other simplices for cosets of parabolic subgroups in a natural way. So let's look at our example again. I wrote down the whole list of all cosets of parabolic subgroups for this example. One has to be a little bit careful because sometimes when we multiply these group elements from the left with the parabolic subgroups, the cosets that we get then can be equal sometimes, but we only, for the simplicial complex that we want to draw, we only want to consider different ones. We don't want repetition in there. So if you notice that some of the cosets are the same, then ignore one of them. We only want to look at the different ones. So in the list you can see in total we get 6 different cosets of maximal parabolic subgroups, and these will then in our simplicial complex correspond to vertices. So now we can already draw 6 vertices. We said that we draw a maximal simplex for each coset of the minimal parabolic subgroup. In the list you can see we get 6 different cosets of the minimal parabolic subgroup, 6 group elements, so it makes sense. So in our complex we would have to draw 6 lines. So we had that our index set for the example had cardinality 2. And that's how you know we have only vertices and then edges or lines. And if the cardinality of the index set is higher, we also call this cardinality of the index set the rank of the Coxeter group, then you would get higher dimensional simplices. This example is rather easy. And now, how do we know where we have to place the lines? A group element is always contained in some coset of some maximal parabolic subgroup. And now, in our example, every group element is contained in 2 different cosets of maximal parabolic subgroups. And now we want that the maximal simplex that we want to draw contains the 2 vertices that correspond to the cosets of maximal parabolic subgroups that contain that group element. It may sound more complicated than it is. If I have the vertex that contains the identity and H, and the vertex that contains H and G, then I want the maximal simplex corresponding to the coset of the minimal parabolic subgroup that corresponds to the group element H to be exactly the line between these two vertices. I think one can see it quite clearly in the picture. So you can see for each line it corresponds to a group element, and the two vertices that the line connects, these always contain the group element that is responsible for this line. And this is how we get the simplicial complex. So in our example, we get a hexagon. And this hexagon is the Coxeter complex for the Coxeter group that is the symmetry group of a regular hexagon. And that is the example. And this is all I wanted to say about Coxeter complexes. And as I said, if we want to obtain an interesting building, a thick building, then we have to glue together several Coxeter complexes. We then also call the Coxeter complexes apartments of our building. And you can't just randomly glue them together, because for a building we need that our simplicial complex satisfies certain axioms. And I will tell you now what these are. So a simplicial complex delta is a building of type Wi, Wi being the Coxeter system, if first it is the union of Coxeter complexes associated to the Coxeter system Wi. Second, if for any two simplices there exists an apartment containing both of them. Third and last axiom, if we have two apartments, sigma and sigma prime, and two simplices, f and f prime, such that f is in sigma and f prime is in sigma prime, then there exists an isomorphism from sigma to sigma prime, fixing f and f prime pointwise. So we start with the Coxeter system, we construct the Coxeter complex, and then we glue copies of this Coxeter complex together, and if in the end what we obtain satisfies these axioms, then we have a building. As a reference, you can maybe look in Abramenko-Brown buildings. There everything is written down in detail. Originally, Jacques Tietz did all the work, all the things. He came up with the notion of a building. And of course, there's also Jacques Tietz obviously wrote about that. So you can also look there. And I think these would be the references that I would recommend. This was all I wanted to say about buildings as simplicial complexes for now. Now that we all know what a building is, I want to define some more words in the context of buildings that will help us talk about things in the future. I want to tell you about projections in buildings, and then what groups of projectivities or projectivity groups are. A building is called spherical if the corresponding Coxeter group is finite. In this video, and probably in most of my other videos that I've done so far, I will focus on thick spherical buildings because these are the buildings I work with the most at the moment. If a building is spherical, then one can show that the apartments are triangulated spheres. And that is very nice. So, if we have a spherical building, that means the corresponding Coxeter group is finite. That means the Coxeter complexes are triangulated spheres, and that means our apartments in our building are triangulated spheres, and that is very, very nice. So focusing on spherical buildings, we can take an apartment, a sphere, and cut it in half. And if we do that, we obtain two halves, and these are also called half apartments. When we do that, I will not give you all of the details, you can read about it, but when we cut an apartment in half, then these half apartments are also sometimes called roots. And let's say this root is called alpha and this root is called minus alpha. Because for a specific cut, we always get the one half and the other half. So alpha and minus alpha, or plus alpha and minus alpha, we call them. And there's always some intersection. And so let's say here the equator, the roots alpha and minus alpha intersect. Then we call all the simplices in the intersection, we say they are in the boundary of alpha and in the boundary of minus alpha. For all the simplices that are not in the intersection, we say they are on the inside of the root alpha or of the root minus alpha. And also sometimes this intersection here, it is called a wall. And these are all very important words that we will need a lot. So take an apartment, and because we are in a spherical case, we have a triangulated sphere, cut it in halves. The halves we call roots, alpha and minus alpha, and where they intersect, it's called the boundary of alpha and the boundary of minus alpha, but also the intersection is called a wall. So suppose we are in our building and we take a root, let's call this root alpha, and we look at the automorphisms that pointwise fix alpha, but also every chamber that has a codimension 1 simplex in the boundary of alpha. Then these automorphisms, if we look at all of them, they form a group. One can show that. And this group is then also called the root group of alpha. We usually denote it by U alpha. And elements of U alpha are also called elations. For a root alpha, we say that alpha is Moufang if the root group U alpha acts transitively on the set of apartments containing alpha. So alpha is a root, so in other words a half apartment, but it can still be contained in several apartments, right? So we want to only fix basically the one hemisphere and then things that intersect here, but we could still have transitivity because this could be in a different apartment as well. And then if we can move here while having this fixed, then we say that the root alpha is Moufang. And a building is called Moufang if every root in the building is Moufang. So why is the Moufang property interesting? Why are we talking about it? In general, given a building, you don't know whether or not non-trivial automorphisms of that building exist. If a building is Moufang, then there are interesting automorphisms because we have this nice transitivity and all that stuff. So a building having a Moufang property corresponds to the building having a rich automorphism group, and that can sometimes be very useful. The word Moufang is the last name of a person called Ruth Moufang. Ruth Moufang was actually the first woman who ever got a proper position as professor in Germany, and she did a lot of work in projective geometry, and there already the word Moufang property has been established. For example, if we think about Moufang projective planes. But now for our building, we also use that word for reasons that I will not explain now. But yeah, so this is where this all comes from. But then also in 1974, Jacques Tietz showed that all thick irreducible spherical buildings of rank at least 3 have the Moufang property and classified them. And then one can also look at rank 2, so all thick irreducible spherical buildings of rank 2. These are generalized polygons, and one could ask, are they also all Moufang or are they not? Can we also classify them? And the answer is, in an appendix of this 1974 lecture notes of Jacques Tietz, he writes that maybe if we look at Moufang rank 2 buildings, then we can also classify them. In general, we don't know if we are given a rank 2 building, if it is Moufang or not, but if we assume it is Moufang, then we can classify. And then he did that later together with Richard Weiss and some help of Bernhard Mühlherr and Hendrik van Maldehem. And then Richard Weiss and Jacques Tietz wrote a book called Moufang Polygons, and this was published in 2002. And there you can find classification for the rank 2. If a building is Moufang, then you know we know that all these nice automorphisms exist, because that is what we always have to show if we want to show the Moufang property, that these automorphisms exist. If we have a Moufang building, then we call the automorphism group generated by these root elations. This we call the little projective group of the building. That is also very important. So given a Moufang building, the group generated by the root relations is called the little projective group of the building. So now why have I told you about the Moufang property if I wanted to tell you about projections in buildings? Turns out that there is some connection, but I will explain the connection way later. Now we will move on to projections. For projections, we need to know what opposites are, because we always take some opposite things in our building and then project. And this is basically how it works, but I will give some more details. So remember, in our nice spherical buildings, our apartments are triangulated spheres, and we can cut them in halves, get these roots, and then the intersection of these roots is also called a wall. If we take two vertices in our building and they are always contained in the same walls, then we say these two vertices are opposite in the building. And now for simplices, let's say A and B, we say that A and B are opposite if the union AB is closed under opposition. And it turns out if two simplices are opposite in one apartment, then they are already opposite in all apartments containing them. So if A and B are in some apartment and they are opposite, if they are also in another apartment, then there they are also opposite. And for maximal simplices, so for chambers, it is the case that the opposite of a chamber in an apartment is unique. Now let's say F is a non-maximal simplex in our building and V is some vertex not contained in F. Then we say that V is joinable to F if the union of the two forms a simplex again. And the simplicial complex induced on all the vertices joinable to a given non-maximal simplex F is also called the residue of F in our building delta. And you can see in the picture, suppose we have that F is the purple line and we have vertices in blue that we can join such that F and the vertices form simplices again. Then the simplicial complex induced on these two vertices, this is then the residue. So the blue area is the residue of F and delta. In our building we can also always measure distances and we use the notion of adjacency for that. So if we have here a chamber C0 and here a chamber Cn and we want to go from here to here, then we can go from chamber to chamber to chamber until we reach Cn, but we are only allowed to go to a chamber that shares a codimension 1 simplex with our previous chamber. So if we look at a rank 3 case that I can visualize in the picture actually, then it would mean that we are only allowed to go to chambers crossing lines. We are not allowed to go through vertices. And this is how we measure distances. And if we then take all of these chambers, C0, C1, C2, blah blah blah, Cn, and we put them in an n-tuple, then this is called a gallery. And now we look at an apartment again, and we take two opposite non-maximal simplices, F and F prime. Then F is contained in some maximal simplex, call it C, and then there will exist a chamber C prime containing F prime that has minimal gallery distance to C. And you can also again look in the picture. So we have our nice triangulated sphere, non-maximal simplices that are opposite, we can take lines, then they will be in chambers. We have the chamber C that F is contained in, and then there will be a unique chamber that has minimal gallery distance to C. And then this induces an isomorphism from the residue of F to the residue of F prime. This isomorphism from the residue of F to the residue of F prime we also call a perspectivity. If we look at the composition of several perspectivities, then we call it a projectivity. If a projectivity is the product of an even number of perspectivities, then we call it an even projectivity. If we start at a certain residue and then we perspectivity, and end again in the same residue, then this is called a self-projectivity. And now the group generated by all self-projectivities of a simplex is called the general projectivity group of that simplex, and the group generated by all even self-projectivities of a simplex is called the special projectivity group of that simplex. Quick recap: if we have a thick irreducible spherical building of rank at least 3, then we have apartments that are triangulated spheres. We cut them in halves, call these halves roots, and we can always find automorphisms fixing one root pointwise and chambers intersecting the root in a codimension 1 simplex, and such that we have transitivity on the set of apartments containing that root. And this is the Moufang property, and the corresponding automorphisms are called root elations, and the group generated by the root elations is called the little projective group. And if we are in a building and we take two opposite non-maximal simplices, then we can project from the residue of the one simplex to the residue of the other simplex, call this a perspectivity. If we have a product of perspectivities, an even number of projectivities that starts and ends, so the product starts and ends in the same residue, then we call this an even self-projectivity, and the group generated by all even self-projectivities of a simplex is called the special projective group of that simplex. And where do groups of projectivities come from? In 1988, Norbert Knarr defined groups of projectivities and special groups of projectivities and determined them for Moufang polygons. And now we, and with we I mean Henrik van Maldenham, Jeroen Schielewaard and me, wondered if maybe it is not only possible for Moufang polygons to determine all these projectivity groups and special projectivity groups, but if it's maybe also possible for higher rank buildings. And then we did that for the simply laced case, and we will maybe still do it for the others. It is the case that we already determined a lot of them, not all of them yet, but maybe we will get there. But while we were looking into that, we also generalized one result by Norbert Knarr, and you can find it in our paper. It is proposition 3.2. And it says, let delta be a Moufang spherical building of simply laced type and F a simplex in delta. Then the special group of projectivities of F coincides with the faithful permutation group induced by the stabilizer of F in the little projective group of delta on the residue of F in delta. And now you can see that the little projective group and this group of projectivities, there's some connection. It was not random that I told you about the Moufang property. And I will tell you more about what all of this means and of the consequences later. And here you can see our table with all the general groups of projectivities and special groups of projectivities that we determined. The next thing I want to do is to tell you a little bit about the history of buildings, where they come from, how did they evolve, how did this all happen. So, if you are a student of mathematics, or you work in mathematics, or you have some interest in group theory, then you might have heard of the classification of finite simple groups. It was a huge thing that many people were interested in over many years. Simple groups, you can view them like building blocks for groups. And then of course, if we understand the building blocks better, then that might help us understand the thing better. So many people were interested in that. Then around 1950, one already knew exceptional Lie groups, but people only ever worked over the reals or the complex numbers. And Jacques Tietz thought about defining analogs for exceptional Lie groups over arbitrary fields. And why was that a thing of interest? Because if we define, or if we were able to find a definition of arbitrary fields, then that would also allow the field to be finite. And with that, one could maybe find a new class of finite simple groups. And then this is why everything was so interesting. Jacques Tits looked at the underlying geometries of these Lie groups and then thought, oh, maybe if he can define the geometries first, then he could also define the exceptional Lie groups or the analogs for exceptional Lie groups over arbitrary fields for these geometries. So he was thinking about geometries. At the same time, Chevalley, so first of all, Brouhard came up with this Brouhard decomposition, and that was very interesting. And then Chevalley looked at that and took that, and he thought about it, and then he was actually able to define these analogs for the exceptional Lie groups over arbitrary fields directly. He came up with a direct construction. So Tits' approach of first maybe finding the geometries was not needed anymore. But then after Chevalley was able to construct these groups directly, Tits looked at them and then he was able to find the geometries. And that is exactly how the theory of buildings evolved, because buildings are geometrical objects, right? And when Jacques Tits defined these geometries, he came up with axioms, and then this is basically how buildings were born. So these groups that Chevalley constructed are also known as Chevalley groups. And like I said, these are analogs for exceptional Lie groups, and now over arbitrary fields. And these we therefore also call groups of Lie type. They have some similarity to Lie groups, but they are not necessarily Lie groups. If we work over the reals or over the complex numbers, Lie group, but over arbitrary fields, groups of Lie type. I will give you some references where you can read up on all these things. It will not be possible for me to explain everything in detail right now at all, but it is known that groups of Lie type have Bn pairs. That is some algebraic property that some groups may have, and if a group has a Bn pair, then it is associated to a building. This is described in the book Buildings by Abramanko and Brown. So there you can read all about that. For Chevalley groups, it is the case that we can view them as automorphism groups of spherical buildings. And they are always simple with some small exceptions. There might also sometimes be some confusion because there is a notion of a universal Chevalley group and an adjoint Chevalley group. What I'm talking about is the adjoint Chevalley group. It was not easy for me to find references about Chevalley groups. One book that helped me a lot was the book Finite Simple Groups by Carter. And basically how we do things is how Carter does things. So we looked at Carter and then how he defines the stuff, this is what we use. These definitions are the definitions we use. And this is basically what I wanted to say about the historical context. Now I will talk a little bit more about what we did and about our article. In our article, we looked at spherical buildings of rank greater equals 3. And we viewed the little projective group of our buildings as the Chevalley group attached to that building. And then in this scenario, the Chevalley group is always simple. And this is how we viewed things or used things and defined things in our article. For Chevalley groups, people are also very interested in the parabolic subgroups of Chevalley groups. So in the parabolic subgroups of groups of Lie type. What is known for these parabolic subgroups of Chevalley groups is that they admit a so-called Levi decomposition. That means you can write them as the semidirect product of a unipotent subgroup and a Levi subgroup. So far, most research focused on the unipotent subgroup, and there was not in every case much or anything at all known about the Levi subgroup. And now one could wonder, why are we not looking at the Levi subgroup? Shouldn't anyone maybe look at the Levi subgroup? And now I'm here to tell you that we looked at the Levi subgroups. So our article was about determining all the general and special projectivity groups for spherical buildings of simply laced type. But with that, we already determined the Levi subgroups of the Chevalley groups attached to those buildings. And I will explain that a little bit. But what we did is we found out about these Levi subgroups. So let me say right now, it is not all very straightforward. I will leave out details, I can't explain it all. If you're very interested, you can read our article. There we explain things in more detail, and we also give a lot of references. So even in the article, it was not possible to explain everything, but we gave a lot of references. So if you are really interested, you can read up on all of these things. So when I talked about groups of projectivities, I showed you many pictures. We viewed buildings as simplicial complexes, and we could see basically, or we could imagine, visualize what happens. And with Levi subgroups or parabolic subgroups of Chevalley groups, we don't immediately have a picture. So one challenge is to see how can we translate all this stuff into things that we can visualize. How can we see the connection between these two notions that we have talked about now. So I said that in our work we view the little projective group of a building as the Chevalley group attached to that building. The little projective group, we already had pictures for that. Now I also said that we are interested in the parabolic subgroups of Chevalley groups. What is now a parabolic subgroup of the little projective group of a building? It is when you pick a simplex F again, and then you look at the stabilizer of that simplex. Then this stabilizer as a subgroup of the little projective group is a parabolic subgroup. So I already told you that in our article we view the little projective group of our building as the Chevalley group of the building. And for the little projective group we already have the pictures, we already know how to visualize that. Now we pick an apartment and a chamber C in that apartment that we will then view as the fundamental chamber. If you don't know what it is, ignore it, I guess. And then we say F should be a face of our fundamental chamber C. So if you didn't know these words, F is just a simplex in our building, right? And now if we look at the stabilizer of this simplex F as a subgroup in our little projective group, then this is a parabolic subgroup. So the parabolic subgroups of our Chevalley groups are the stabilizers of simplices in the little projective group. And now let's denote the stabilizer of F as a subgroup in the little projective group as GF, so the group GF. One thing that is also known is that the parabolic subgroups opposite GF correspond bijectively to the Levi subgroups of GF. So a Levi subgroup fixes a certain simplex and a unique opposite simplex pointwise and acts as a group of automorphisms on the residues of these simplices. So a Levi subgroup fixes a simplex and a unique opposite simplex pointwise and acts as a group of automorphisms on the residues of these simplices. And I already showed you our theorem that illuminates the connection between the little projective group of a building and the special group of projectivities of a building. And now if one thinks about things a little bit and writes them down in a nice way, in a structured way that makes things clearer, then one can see that the Levi subgroups of the Chevalley groups are just exactly these stabilizers. And since we have this nice connection through our theorem, we can see that if we determine all of these projectivity groups, then we also determine the Levi subgroups. I must say though that this is basically impossible to understand with just this video. I can't explain everything that is going on in this video, and there's a lot going on, but like I said, you can read the article if you want. We give a lot of references there. I will try to give references, but it is not possible for me to explain everything about this in depth right now. And if you don't understand, or you don't feel like you understood, it makes sense, because I don't think you can understand all of this just with the information I gave you right now. It was just to tell you a little bit about the group theoretic consequences of the research that we have been doing, just so you can get an impression, you know where things came from, you know a little bit more about the motivation, but I mean, probably this is not for understanding in detail. I will shortly show you the table that we came up with that lists all the different buildings and different residues one can look at, and then all the general groups of projectivities and special groups of projectivities. So all the things we determined, all basically the essence, everything that we worked on is more or less summarized in that table. But also, again, you will maybe not understand where this table came from. It will be impossible to understand where this table came from and how we did that by just watching this video. Unfortunately, I will also not explain any of the proofs or technique we use to determine these groups of projectivities, because we used so many different tools and proved all the things in so many different ways that it just doesn't fit inside one YouTube video. It also, we use a lot of incidence geometry again, and then we use a lot of facts about parapolar spaces and all that stuff, and I don't have the time and space here to explain everything. So this video was about telling you what a building is viewed as a simplicial complex, explaining to you what the little projective group of a building is, what the Moufang property is, why we are interested in that, what the groups of projectivities are, and then I want to tell you that, look, we determined them, these are the results, this is what we've been working on, this is my update about my research for you, but of course you will not understand how, because there was a huge jump now. I defined groups of projectivities and then I showed you this long table, and in between there's a lot that I just do not talk about in this video. So just to make that clear. So I will now show you our table. This is our table. It's a long table with a lot of PGL in there, but not always PGL. There are some special cases that are quite interesting. Yeah, and these are our results. You can look at them. Very nice. Thank you very much for your attention. So this is all I wanted to talk about today, just to give a quick update on our research and maybe saying a bit about our article, but also not too much, just explaining the basic concepts that are needed to understand the article. So now, after you watch this video, maybe you can read the article and then it will be easier for you to read it. Thank you very much for watching and goodbye.